Hello students, let us start our new session of chapter 10, Mechanical Properties of Fluids. Now let us understand Stokes' law. When a body falls through a liquid, it drags the layer of fluid in contact with it. So the relative motion between the different layers of fluid is set and it generates a retarding force. For example, falling of raindrop, swinging of pendulum bob. This viscous force is proportional to the velocity of the object and opposite direction of the motion. That generated force F depends on viscosity coefficient eta and radius of sphere A. So the viscous force, drag force F equal to 6 pi eta A V, which is known as the Stokes' law. Here no derivation is required. So here if a raindrop is available in air, is accelerate initially due to gravity. So as the velocity increases, retarding force also increases. When viscous force plus buoyant force is equal to the force due to gravity, the net force becomes 0 and the acceleration becomes 0. So the raindrop descends with a constant velocity. So in equilibrium, at the thermal velocity Vt, it is given as 6 pi eta A Vt equal to 4 pi by 3 A cube rho minus sigma g, where rho and sigma, that is a mass density and mass density of sphere and fluid, and Vt, the thermal velocity, equal to 2a square rho minus sigma into g divided by 9 eta. This thermal velocity depends on the square of the radius of sphere and inversely proportional to the viscosity of the medium. Let us go through the example regarding the Stokes' law. The thermal velocity of a copper ball of radius 2 mm falling through a tank of oil at 20 degrees Celsius is 6.5 cm per second. Compute the viscosity of the oil at 20 degrees Celsius. The density of oil is 1.5 into 10 raised to 3 kilogram per meter cube. Density of copper is 8.9 into 10 raised to 3 kilogram per meter cube. So here thermal velocity Vt is given 6.5 centimeter per second. Convert into the meter per second, that it would be 6.5 into 10 raised to minus 2 meter per second. A, the radius of sphere, the copper ball, is given 2 millimeter. Convert into the meter, it would be 2 into 10 raised to minus 3 meter. G, that is 9.8 meter per second square, and density of copper is given 8.9 into 10 raised to 3 kilogram per meter cube. And density of oil fluid is given sigma equal to 1.5 into 10 raised to 3 kilogram per meter cube. So from the equation of thermal velocity Vt equal to 2a square rho minus sigma into g divided by 9 eta. From that make the subject of formula eta, then it would be 2a square rho minus sigma g divided by 9 Vt. So substitute all the values, all the terminologies are given, and eta would be equal to 9.9 into 10 raised to minus 1 kilogram per meter into second. Now Reynolds number. Here when the rate of flow of fluid is larger, the flow cannot be remain constant, cannot be laminar, and it becomes turbulence, as we can see in the diagram. This is what initial lines are constant, gives you the laminar flow of fluid, and then it becomes turbulence. This turbulent flow of velocity of fluid at any point in space varies rapidly and randomly. It also gives some circular motions and eddies. So if an obstacle placed in between the path of fluid while fast moving fluid is there, it will give you the turbulence motion, as we can see over here in the diagram. So like the smoke rising from a burning stick of wood, ocean currents, these are turbulence. Twinkling of stars, that is due to the atmospheric turbulence. Waves in the water and air left by cars, aeroplanes and boats, these are the results of turbulent. Reynolds observed that turbulent flow is less for viscous fluid flowing at low rates. He defines a number which is a dimensionless number whose value gives an approximate idea the flow would be turbulent. And this number is known as Reynolds number, Re, equal to rho V d divided by eta. That rho is the density of the fluid, V is the velocity of fluid, d is the dimension of pipe, and eta is the viscosity of the fluid. Re is a dimensionless number and it's same in any system. If this Reynolds number Re is less than 1000, then it defines that flow of fluid is streamlined or laminar. If Re value is greater than 2000, then it defines that flow of fluid is turbulent. And if Re, Reynolds number in between these two limits, 2000 to 1000, then the flow of fluid becomes unsteady. So Re, the value of Reynolds number, that is a critical Reynolds number at which turbulence is set, is found same for the geometrically similar flows. For example, when oil and water with the different density and viscosity flow in a pipe having the same shape and size, then turbulence sets, that is with the same value of Re. This number is useful to design ship, submarine, racing cars and aeroplanes. Re can also be written as rho v square divided by eta v by d. That would be equal to rho av square by eta av by d. That is the inertial force divided by force of viscosity. This represents the ratio of inertial force, that is force due to inertia, that is because of the mass of moving fluid, to the viscous force. This turbulence gives the kinetic energy, and this kinetic energy convert into the heat. So racing cars and planes are, for that precision is required to minimize that turbulence. Like a friction, this is undesirable. It also required in many of the applications, like in mixing, increase the rate of mass and momentum of energy. In blades of a kitchen mixer, that the turbulence flow will provide the proper mixture and thick puree. Example, the flow rate of water drop a tap of diameter 1.25 centimeter is 0.48 liter per minute. The coefficient of viscosity of water is 10 raised to minus 3 Pascal into second. After some time, the flow rate is increased to 3 liter per minute. Characterize the flow for both the flow rates. The speed of flow V for the diameter is given 1.25 centimeter. So the volume of water flowing per second, that Q equal to V into pi d square by 4. So V equal to 4Q by d square into pi. So Reynolds number Re equal to 4 rho Q by pi d eta. Here all the values are given. Rho is given 10 raised to 3 kilogram per meter cube. Pi 3.14. Diameter is given 1.25 centimeter, converting to the meter, and eta is given 10 raised to minus 3 Pascal into second. Substitute the values, so you are able to get Re equal to 1.019 into 10 raised to 8 meter cube into second into Q. Initially, the value of Q, that is the flow rate of water, is given 0.48 liter per minute. Convert into the meter per second. So here 8 into 10 raised to minus 6 meter cube per second. By replacing the value of Q, Re equal to 815. And Re below 1000, it means flow is steady. Now the next value of the Q is given 3L per minute. Convert into the meter per second, that would be 5 into 10 raised to minus 5 meter cube per second. By substituting the value of Q in Re equation, it will become 5095. That is greater than 2000, it means the flow of water now becomes turbulent. So here that is available in the wash basin that determines the transition from laminar to turbulent flow. Next, surface tension. This gives the surface of the fluid processes by some additional energy, that is known as surface tension, that is concerned with liquid only, not fluid. In fluid, liquid and gases both are included. This surface tension is applicable only for liquid. So here this liquid stays together because of the molecules are available nearby to each other based on its attractive force. So here intermolecular distances are such that they are attracted from its surrounded molecules, as you can see in the diagram A, which gives you the negative potential energy for the molecules. That depends on the number of molecules and distribution of molecules around the chosen one at the center. Its average potential energy will remain same. So here the collection of molecules and the disperse of them far away to each other will give you the evaporation, which required heat to evaporate in a larger value. So the water that is available 40 kilojoule per mole. In diagram B, as you can see, only the lower half of it is surrounded by the liquid molecule and above part having air. So here the negative potential energy available, but that is less than the molecule in bulk. So molecule on a liquid surface having some extra energy in compared to the molecule in bulk in downward side. So molecule on liquid surface having the larger energy tends to have, that liquid tends to have least surface area, which increase the surface area requires energy. It requires So here liquid tends to have least surface area with external conditions permit. Increasing surface area require energy. It means the half of the energy requires to remove it entirely from the liquid, that half of the heat is required of evaporation. And a liquid consists of molecules are about cannot be perfectly sharp surface. Density of liquid molecule drops rapidly to zero around Z as we move at the upward side, as we can see in the diagram C. So here the distance of order of few molecule sizes. Here, as you can see, an extra energy is associated with the surface of liquid that create more surface or spreading of surface by keeping other quantities like volume fixed, apply the additional energy. So here in the diagram you can see that horizontal liquid film ending in bar and free to slide over the parallel guides. So move a bar by a small distance d, the area of the surface is increases. The system has more energy, means work has been done against the force. The internal force is F, so work done is F into d. From the conservation of energy, it stores an additional energy. If the surface energy of the film is S per unit area, then extra area is twice dl. So film has two sides of the liquid in between. So here there are two surfaces and extra energy, that is S into twice dl equal to work done Fd. So S equal to Fd by twice dl or F by twice L. So S is the magnitude of surface tension, that is equal to the surface energy per unit area of the liquid interface, and that is equal to the force per unit length exerted by fluid on movable bar. So here we consider fluid surface in contact with other fluid or solid surface. That surface energy in that case depends on the material on both the sides of surface. If the molecules of materials attract each other, surface energy is reduced and they repel each other, then surface energy is increased. So surface energy is the energy of the interface between two materials and depends on both of them. So here we can say that surface tension is the force per unit length or surface energy per unit area acting on the plane of interface between the plane of liquid and any other substance. It also is the extra energy that the molecules at the interface have to compare to the molecules in the interior. Second observation, at any point on the interface beside the boundary, we can draw a line and imagine equal and opposite surface tension force S per unit length of the line, which is acting perpendicular in that plane of the interface. So this line is equilibrium. The line of atom and molecule can be at this surface. This atom left pull line towards them, those right towards them. So this line of the atom is in equilibrium under tension. if the line really marks the end of the interface, so here the force S per unit length acting inward side. Here in the table, the surface tension of some liquid is given based on the temperature which required for the vaporization. Viscosity, just like a surface tension of a liquid, is falling down with temperature. Here, a fluid will stick to a solid surface if surface energy between the fluid and the solid is smaller than sum of surface energy between solid air and fluid air. So here cohesion between the fluid, a solid and the fluid, we need to consider a vertical glass plate below which a vessel of some liquid is kept. This forms a one arm of balance to measure the surface tension, as you can see in the diagram. The plate is balanced by weights on the other side with its horizontal edge over water. The vessel is raised slightly till the liquid just touches the glass plate and pulls it down little because of surface tension. Now weights are added till plate just clears the water. So that additional weight is required, for example, W at the other side. So the glass plate becomes at the surface of the fluid. This surface tension of the liquid air interface is SLA, that surface tension between liquid and air. That would be equal to W by twice L. That would be equal to mg divided by twice L. Well, m is the extra mass and L is the length of the plate H. LA gives the surface tension between liquid and air. Here we are going to end the session. Hope you understood. Thank you.